Hello everyone. So welcome back to this channel. In the last video, we were discussing um, mutually exclusive, mutually non-exclusive, mutually independent, and mutually non-independent. And we slightly touched upon um, mutually how a mutually non-independent events are considered as a conditional probability. So in continuation to that, in this video, we are going to discuss about more in detail about conditional probability, a couple of problems, and how this conditional probability is taken to uh, Bayesian theorem. Okay, that is the agenda of this discussion. Those who have not watched the earlier discussion on mutually exclusive and mutually non-exclusive, mutually independent and mutually non-independent, it is highly recommended. Please watch that video and come back to this for a better clarity. So we have discussed A and B, the two event, which is not independent. Okay, the occurrence of one event can influence the occurrence of another event. How do we represented this? We have, if the event A influences event B. We have the last section we have discussed. If you get up late in the morning, how it influence uh, the you reach office late, how it influences that, how do you reach office on time, or you're reaching office late, it's influencing that, right? So B bar E. Suppose if the event B influences A, you can represent the conditional probability here, P of A, in which B event has already happened. The slash A and slash B, it indicates that it is the event A is already happened, which is influencing B. Similarly, B already happened, which influences the A event. Now I can have two expression, right? I can have two expression. One is probability of A bar B. Okay. You just bring this P of B below this A intersection B. I can represent probability of A intersection B divided by probability of B. Similarly, by keeping this term in the right hand side, so bring down this P of A below A intersection B, you can have another expression, something like this. B bar A equivalent to A intersection B divided by P of B. Okay, these two are two ways of representing a conditional probability. Can represent this in two ways. So let us do a simple example problem. As we discussed, this mutually independent and mutually independent uh, events and its calculations are basically more practical, and it is the calculation is done primarily based on the historical data, empirical data, basically. Assume there's a historical data which says I have smoking person and non-smoker and it's their corresponding health status in a particular clinic. Assume it is a cancer, healthy. Typically, this representation is called as a contingency table in statistics, or in data science, we used to call it as a contingency table or crosstab table. So both are categorical variables, right? Qualitative variable. A person is having a cancer or healthy. A person is having a smoking habit or is a non-smoker. So you can have this crosstab table based on your historical data, and my count is like this, and this is my count. So there are 200 cancer cases are there. Out of 200 cancer cases, 150 are smokers and 50 were non-smokers. Similarly, I have 1,300 healthy people are there, out of which I have count like this: 500 smokers and 800 non-smokers. So it entitles to the total number of smoking candidates or 650. If you see the row total, and similarly here it is 850, right? And this is the grand total. So 1,300 plus 200, 1,500. Similarly, 650 plus 850, if you see 1,500. Generally, any historical data, when you pick two qualitative variable, one is the category whether the person is a cancer or is a non-cancer. Rather, using the word healthy, non-cancer could be the better. Because you might think that how come the people who do smoking 500, how they could be healthy? Maybe they don't have cancer, this particular cancer, but they could have different kind of breathing related disorders, like some other lung problems. Definitely, no. Rather, using the word healthy, we could say they don't have cancer, non-cancer cases, cancer cases and non-cancer cases. That could be the apt term. Okay, cancer or non-cancer. So having this empirical data, suppose I wanted to write a conditional probability statement. What is the probability of a person likely to have a cancer if he is a smoker? Okay, given a condition, he is a smoker. He's a smoker. This is a smoker is a particular event which influences the another event, cancer. So we have the prior statistics. The details are here. So how do we estimate a new person? He is likely to a person entering into the clinic and he reports he is a smoker. And what is the chance that he is likely to be a cancer? He is having a cancer. So based on the conditional probability, how do we write the expression? So probability of A bar B, how do we return the expression? Probability of A intersection B divided by probability of A. So the similar manner we can write probability of cancer intersection smoker divided by probability of smoker. So from the contingency table or crosstab table, you can, however you can call this, okay, you can pick the score cancer intersection smoker. So the cancer intersection smoker is, this is the value, right? So out of 1500 cases in the prior data, historical data, 150 records, these two conditions satisfies, right? A person having a cancer and he is a smoker, 150 records, that is the intersection, common. So in the numerator, I'm going to substitute 150, okay, 150 out of 1500. And the denominator, what is the probability of the smoker in the historical data? Okay, the total number of smoking records are 650, right? This is your row total, the smoking 650 out of 1500. 650 out of 1500. So you can get 150 by 650, 15 by 65. So if any person who's reporting as a smoking habit, what is the chance that he is likely to have a cancer based on this historical data? Okay, based on this historical data, maybe this historical data is pertain to a particular clinic, and that particular clinic is uh, with pertaining to a particular geographical location. Mostly it reflects the characteristic of the smokers in and around that region, geography, right? So it influences majority that these cases has a similar kind of eating habits. All these cases have experienced living in a similar kind of environmental conditions, and so many other factors is we are considering as all are similar uh, characteristics pertaining to that particular geographical location. So having said that, any new case, if any new person who's entering into the clinic and he wanted to have some kind of medical check, and based on the historical data, what we can conclude, a person with a smoking habit, how likely to he is going to have cancer. So we can say 15 by 65. 15 by 65, it is around 23 percentage, right? Roughly, is having 23% chance to have a cancer. So this kind of no real world in applications, we can make use of this conditional probability. So after understanding this conditional probability, Bayes has come up with a very interesting relationship he established. Most of the real world problem, okay, most of the real world problem, we can generalize this conditional probability. What Bayes has generalized this conditional probability with a very beautiful expression like this. So first I'll tell you how this expression is, he has arrived at that expression is based on our earlier two equations only. So two equations we have written, right? Probability of A bar B. Once again, I write those two equations. Probability of A bar B. Probability of B bar A is represented as, it's a B intersection A or A intersection B, both are same, right? P of A. So P of A intersection B can be represented as two ways. One is A bar B, another is B bar A. Okay, let me call this is equation 1, this is equation 2. I'm going to equate P of A intersection B. Okay. Take as a cross product and equate both the equations. So from the first expression, how I can write? From the first expression, I can write it like this. P of A bar B times P of B, okay, is equivalent to Similarly, P of A intersection B, from the second expression, I'm going to write like this. P of B bar A times P of A. So keep P of A bar B here, take this P of B to the denominator. So we can have our final expression like this. P of A bar B is equivalent to P of B bar A, B bar A into P of A divided by P of B. Okay, Bayes has arrived this, just simply he related these two conditional probability and he has arrived a relationship between P of A bar B and P of B bar A. This is a new relationship he just established based on the two conditional probability equations. So how he is generalizing this relationship, what is the use of this, practical use of this relationship if you ask? Okay, I'm going to write this expression, in generalized form, like probability of hypothesis evidence bar hypothesis into probability of hypothesis divided by probability of evidence. Of course, in our probability and statistics for the data science, it's a series of lectures. I'll be discussing about hypothesis testing for different cases. We'll discuss in detail. Okay, however, here we can understand that hypothesis is something we are trying to prove, okay, with the available data. So this is the, provided the evidence is given, okay, if the evidence is already available, if evidence is available, and what is the probability of a hypothesis? This is what we are intended to measure, okay, and already from the historical data, we were able to measure this. Some of the business problem, we were able to measure either probability of evidence versus certain business problem, we were able to have beforehand, we could measure this. According to the business context, which is measurable, we have to see which quantity is measurable, and that measurable quantity we have to put it in the right hand side, and we can estimate this one. So to understand this, let me take a simple example so that we can understand this Bayes theorem very well. We can appreciate Bayes theorem very well. As I told you, the Bayes theorem became very popular the moment it showcased its practical usage in spam email filtering. Let me consider. Okay, assume that I have manually filtered. Okay, I have manually filtered each and every email before applying Bayes theorem filtering. So totally, I have worked with around 600 emails. Okay, totally, I assume that I have totally 600 emails. Out of the 600 email, assume that manually I have filtered by checking each and every email, whether it is a spam. If it is a spam means I just put it in the spam folder. If it is non-spam, I'm going to put it in the non-spam folder. Okay, non-spam. So let us assume because spam email may contain different keywords like money, lottery, okay, prize money, these kind of things used to come, sales, okay, buy. These are all some keywords. Based on that, we can, how do we manually, we assume that manually I have filtered certain, based on, by reading the complete email, I can understand these mails are spam. These mails are spam. So manually, I'm allowing, after reading the content, I just put these certain emails are in the non-spam folder. Okay. So manually I have did it. Now I want to automate this process. Okay. This is going to be my historical data. What I have done manually for so far with 600 emails, it is going to be my historical data. From that, we are going to understand a certain relationship, and we are going to use that statistical relationship to predict the future email, whether it's more likely to be a spam or non-spam. Okay, that is the fundamental idea here. Okay, with the sample data here, my sample data is 600. We are going to predict for the future. We are going to make the inference, statistical inferences using a simple Bayesian rule. So after manual filtering, I notice 20% of the emails comes under spam list, and remaining 80% of the email were genuine non-spam. So totally we have 600 emails, right? You have done it manually. So 20% of 600, 120 emails were collected here, and 480 emails are collected here. 480 emails, here we have 120. So in this whole process, what we have collected the informations. So the probability of spam email is 20%. Of course, this is measurable from this. And for this example, let us assume a word, keyword. Uh, what I would like to uh, predict here, I would like to predict what is the probability a new incoming email with the keyword, okay, with the keyword money. Let us say it's a money. What is the probability that particular new incoming email is likely to be spam? So you try to write this relationship based on the Bayesian rule, like a hypothesis bar evidence. Here, what is the evidence? Evidence is money is the evidence you just see, and you need to calculate what is the probability of that based on this evidence. You are going to predict what is the probability this particular mail is more likely to be a spam or non-spam. Because there are some genuine email also can contain the word money. Okay, so that's what the statistics tells. So additional information, what is the statistics tells here? You're counting what is the total probability of occurrence of the word, okay, of the word money from your database, from your 600 email database. The probability of the money occurrence, it's 25%. Okay, the total probability of occurrence of the word money, or in other way I can say that the probability of the email containing the word money is 25%, irrespective of spam and non-spam. And once you segregated this emails, like this one, you segregated the email based on the different criteria. One of the spam mail could have a word lottery, another email could have a money, prize money, and so many. Okay. Out of which out of this 120 records, I found, okay, because this is measurable, right? For me, it is measurable. What is measurable? I'm going to measure what is the probability of occurrence of the word, okay, for the word money, provided it is in the spam folder. Since already you have manually you have done this spam folder and non-spam folder, you only filtered, and you got this 120 emails are here. Out of this 120 emails, there are certain emails are related to lottery keywords. Some emails are related to purchase this spell, purchase this lottery money, buy. So proven already it is the spam folder. There is the event already happened spam. Okay, that is what proven something already. It's a hypothesis. What is the evidence? Here the evidence is you are seeing the evidence, whichever the email containing the word money, that is measurable. That is found to be 90%, assume. 90% means 108 emails. Out of 120 emails, 108 emails are containing the word money. That means remaining 12 emails containing other keywords. Okay, there may be other keywords, but those remaining 12 emails also, it is a spam mail only. So these are the prior statistics I know. Okay, probability of spam is overall email 20% is spam. Out of the 20%, 90% of the email containing the word money. So these are all measurable. Okay, the total probability of occurrence of the word money is 25%. So having this information in our hand, now we can easily relate this like probability of, okay, probability of the word money proven already it is a spam. Okay, that is equivalent to probability of evidence by hypothesis into probability of spam divided by probability of the word money. Now in the right hand side, whatever the information I have written in the formula on the right hand side, all are measurable based on the empirical data, based on the historical data. Just I need to plug in all these values. So probability of the word money, provided it is proven as a spam, that is probability of evidence by hypothesis. This information already we know, which is 90%, right? So substitute this 0.9 into probability of spam 20%, 0.2 divided by the overall probability out of the overall total email. The probability of occurrence of the word money is 25%. I plug in all these values, and if you simplify, this is found to be 72%. So what is the probability if a new incoming email with the word money, how likely it is belongs to spam folder is 72%. So people will build this Bayesian theorem, Bayesian rule based spam filtering. They can give a different cutoff of this probability. If the probability is greater than 75%, if the probability is greater than 80%, then they can put that that particular email into the spam folder. Otherwise, they don't put it in a spam folder. So that cutoff can be decided by the people who would like to automate this process. Okay, that is their designer's choice, this cutoff. So this is the idea of Bayesian theorem, how it extends your conditional probability, and it is trying to bring some relationship between probability of hypothesis bar evidence or probability of evidence bar hypothesis. So you can relate this expression to any business problem. Your business problem, you can relate it based on the historical data. You can predict the future incoming data based on the historical data. It's a classic example of inferential statistics using a simple Bayes theorem. So once you understood this, okay, in the next video, I'm going to talk about. Now we have discussed all the basics requirement of your probability. Also, now in the next session, I would like to extend this idea towards whatever the variable we have analyzed. Okay, whatever the variable we are going to analyze, which comes under two categories. Either it is going to be a qualitative variable, qualitative, or quantitative variable. If it is a qualitative variable and whatever the probability I calculate, okay, that probability is generally represented as, okay, the distribution of that probability is represented as Okay, discrete representation. Discrete representation. Such representation is called as probability distributions. And for quantitative variable, continuous variable, your x-axis is continuous. So you will get a continuous probability distributions. Continuous probability distribution. So the classic example is for the continuous variable, quantitative variable, normal distribution. We talk about normal distribution. For discrete distributions, for qualitative variables, we talk about two popular distribution. One is binomial, another is a Poisson distribution. Binomial, Poisson distribution. Again, how this is going to be helpful in how it is going to take a part in inferential statistics. So what is the scope of understanding this distribution? In what way this understanding this distribution will help us to take to the next level inferential statistics. In fact, we are going to do the hypothesis testing, which is going to lead to hypothesis testing. So these are all the building blocks. These are all the building blocks to understanding the probability first and its distribution, and how we take it forward to inferential statistics. In inferential statistics, we have different stages to of estimation. Okay, so those stages we used to represent with the different statistical tests and all. To understand those statistical tests and all, these fundamentals is playing a very crucial role. Okay, with this today's session, I'm going to stop in this video. So the forthcoming session, we are going to discuss about the probability distribution of these three cases and its connection with respect to the inferential statistics. Inferential statistics. See, the broader picture is, we should not forget, the broader picture is inferential statistics. Okay, that is our broader picture. So with that goal, we were studying at the different building blocks. In the previous video, we studied about the different types of probability and its calculations. And extension to that, in this section, we discussed about conditional probability and Bayesian theorem. And in the subsequent session, we are going to talk about the different probability distributions. Okay, I will meet you in the next video soon. All of you take care.